Okay. At least we have one. This is something which we have done. Let me come again. Mohan. Mansoor. Varda. Reha. Hassan. Is you?
Yeah.
To make sure it has been entered in your in the blackboard. So yeah, your grades are entered in blackboard before we give it back to you. So maybe you need to keep on tracking if the score is uploaded. Right score under the right assignment. There should be one more. Jewelry. Young. And Charlie. Again, homework with no name. So that's like a trademark or something?
No, I just didn't realize I need to enter my name when I'm uploading on Blackboard because you already know
Right.
it that it's mine. So.
We print it out.
Yeah, I didn't know that. Then you'll be printing it out and then reading it.
Okay.
Don't rely on technology.
Huh?
I learned the hard way. Don't rely on technology to maintain
We
metadata.
have to name it, but just put something somewhere. So let's see if we can do the touchpad thing. All right, so we are back. So we looked at implantation aspect, right? So slightly different mechanism for these ionic species, very different factors that contribute to how deep we can get them and what kind of profile we get from ion partition. Then diffusion. Channeling is something which you are looking at. You say, okay, we can avoid it by giving an angle to the wafer. So this is something which we see channeling is reduced by putting a screening oxide. So scattering them before they get to the substrate can also reduce channeling because instead of falling straight down, or they will have much more deflection before they settle. So this is just image from the previous slide. Just showed that this is where we get the angle to the substrate, and essentially this is a very simple schematic showing how the beam travels during the machine. So we vertically scan it, horizontally scan it, have a mask through which we define the wafer, and there we give it tilt or twist. Right. So we may not have a mask at all, so we would just strike it directly on the wafer. Right. So this is stuck. So get back to this guy. So we can default. So we can tilt the angle, we can deposit a screening oxide, or we can amorphize the surface, which is, what is amorphous material?
It has no exact shape.
So we can what you call break down the crystalline structure at very close to the surface. So that will result into very reduce the channeling effect.
What is pre-amorphizing?
So amorphous, making a material amorphous.
So pre-amorphizing.
So before you do the process, we amorphous, make the surface amorphous. So that's pre-amorphization before you do the implantation. So that can be achieved by low energy silicon or germanium implant. So essentially we are giving implanting semiconductor material in semiconductor material, right? So we are implanting silicon into silicon, crystalline silicon, which is resulting into amorphous surface, amorphization close to the surface, which will result into reduction of channeling. Right? So there are different amounts of silicon dioxide that can provide different amount of channeling. So reduce the channeling effect. So your profile is very linear with that. So we don't need this guy. So what happens if we use high angle? So we can control the dopants with much less underlapping of the structure. So we can make something like this where, so this can be a structure which can be made in hard material oxide or can be photoresist. So we can control exactly where the doping stays, how far it gets below something. But then that is also negative for shadowing, right? So to get dopant below a structure, we can use angle, but then that causes it to shadowing effect. So it can work for our advantage, but then you have to provide that rotation effect or implant it from four sides so we can get the same amount of implantation on all sides. So this is something that shows that at different angles what kind of depths we can achieve. So if we use 86 degree, we can have a depth of close to less than 50 angstrom. Is this good or is this bad? Now, after seeing so many things, what do you say? Achieving this kind of profile at such a close depth, small depth, is it good to have it or is it bad? Yes.
I don't think it's good.
Don't think it's good? We are maintaining that profile very close to the surface. So junction depth, think what junction depth. Junction depth is increasing or reducing? Reducing. So if your junction is too thin, what kind of doping do we need? Something which is very close to the surface, right? Which maintains the concentration, which you cannot do with the diffusion, right? So here we can do that. We can maintain that depth very close to the surface. We can maintain that concentration very close to the surface. Right? Does it make sense? So this gives a spike. So this is something that what we call in case of diffusion. There was this a type of diffusion where we instead of pre-dep, we implant those and then we diffuse them. So we have them very close to the surface. What was that called?
Pre-dip, then driving.
There was a special type of diffusion where we would do implantation and then do dry with dead. transient enhanced diffusion. We have exam after 2 days, so that would be part of it, I guess. And again, there's just 30% have asked for take home, so I'm dropping the idea of take home at all. I didn't get everybody to be the same. Okay, what happens to the crystalline structure when the high energy ions they collide with atoms? They displace them from the lattice space. So those sites where they are, those are low energy sites. They are the minimum energy sites. But when they're displaced, they would result into, they would impede the flow of charge, right? So they'll be acting as collision sites. So what we need to do is we need to bring them back to the lattice, so we can, what we call, activate, electrically activate those lattice sites. So that is done by Freudian heat, by heating it, what we call as annealing. So after implant, we have to do annealing. What it does is heals the damage of the lattice and makes the dopants electrically active. So once we do the annealing, there are still some defects, but they are too few than what they were before annealing.
And electrically active lattice site would be what?
So they knock off the position where the silicon was, but they don't get to their actual position where the silicon used to be. So when we do the annealing, they fall into those places where they contribute acceptors or donors. So before annealing, the ions don't contribute as they're supposed to be with that concentration. So once we place them at the lattice position, then they are electrically active. Then their contribution becomes what we are expecting at that concentration.
So it can't bond to the other electrons if it's slightly away from where it's
If it's not at the lattice point, right? So whichever it may be, corner or maybe tetrahedral, it will not be contributing the charges that it's supposed to be. So so if you remember the crystalline structure, how do electrons or holes get contributed? They have to be in a sort of position where they share all their electrons with the neighboring atoms, right? And then excess or reduction of electron results into charge transfer. But if they are not at those positions which are equal distant from all the neighboring atoms, they will not be contributing those atoms. So they have to get to the position of the lattice where they can then start contributing their excess of electron or reduced number of electrons, just holes, right?
So before anything, they don't contribute as carriers.
There will be very few who will be active, who would have reached their positions where they will contribute charge carriers. There are very few of them. So we have to get all of them to do that. That's called annealing, to activate them, activate the dopants. So there's nothing like switching on and off, but we provide enough heat so they can fall into the lattice place to start contributing their electrons or holes. Right? So annealing, what are the two actions that annealing does? What are the two things that we do with annealing? Heal silicon and activate dopant. Always remember there are two effects that we get from annealing. So what are those damages? They are point defects or clusters of point defects. Now remember that when we talk about defects, they are always physical anomalies, physical damage. But when we have physical damage to a crystalline structure, we don't get what we want from that crystalline structure, because then atoms are not contributing their electrons or holes to the flow of charge. If that doesn't happen, our device don't behave the way we want it. Our device doesn't behave electrically the way we want it. So defects result into degradation of the device performance, right? So device, what do we measure from device? So if you have a transistor, what are we supposed to measure from a transistor? What are we supposed to get done from a transistor? Flow of current, right? When we do gating, we want to see that current flow. If there are defects, we don't see that, or we don't see the current that we would expect to flow, or we don't have control of the gate over that on and off of the circuit. So these physical defects translate into electrical behavior of the device. So there can be what you call point defects or clusters of those defects. Can be zones of amorphous material, and amorphous is where there is no crystalline structure, where there is no repeatability left now into when do those atoms occur in that structure, right? So amorphous material doesn't have any crystalline structure. So I may start with crystalline silicon, but if I have too many silicon around, floating around that structure, essentially for charge carriers, it's an amorphous material. It loses the crystalline properties to it.
Basically, if you bombard it too much, you break the crystalline structure.
It's not always if you bombard too much. So there are many reasons why this would happen. Maybe, so we'll see where does it come from. But in any case, we do the annealing, which recovers most of that for us. Right? So, and that can be localized zone, or it can be whole layer of amorphous material. And of course, light ions will do less damage than the heavier ions. Right? So if you look at the light ion, it's gonna keep on bumping into the atoms, and it's gonna end up into some position. So these can be isolated defects, or it can be a cluster. But if it is a heavy ion, it's going to result into a big area of defects. Right? So in this case, which is 50 angstrom, 5 nanometer wide. So if your channel length is tens of nanometers, and you have 5 nanometer of that defected, so you can imagine that how device would behave. And there's more damage when nuclear stopping dominates, and we know that that's a mass phenomenon, right? Nuclear stopping happens when there is a energy transfer due to collision, and not because of just electrostatic transfer, right? So this happens at the light ion profile and beginning of heavy ion profile. So we know that this nuclear energy transfer, nuclear stopping is dominant when the light ions finish their trajectory, and heavy ions at the very start. So of course, more dose gives us more damage, right? So this is just an example showing that the high dose can result into this whole region to become amorphous than the rest of the material. And we don't want it to stay amorphous. So boron and arsenic, their damages with respect to the trajectory, so projected depth, right? So we expect it to have a profile at certain depth, but that same depth will have the density of those defects, right? So which will peak at some depth, right? So if the energy goes high, so we see the profile is very sharp, but for lower energy, that is shallow as well as it's expanded. So for both of the cases, that's different. Now, arsenic is a light, is a heavy ion than boron. so which results into much more expanded trajectory of the damage than boron. Right, so this is also normalized, so whites is also normalized. So this is where you will have the depth at which you want the maximum of the doping profile to occur, so this will occur around that, both sides of that one. How does it look physically? So this shows that there are different amounts of doses have been used of silicon and silicon. And if you see that as the density increases, is it visible? Visible to me here. The thickness of the amorphous region increases. So this is just this much from here to here in this case. From here to here. Yeah, you can see the arrow or not. So this is slightly more, in this case, gets even further. Let's see. So this is maybe you can see that. One. So that increases. So in this case, this is the whole region which has become amorphous with silicon. So what annealing does is it takes care of the crystalline damage, point defects and clusters. So if you heat it, so different temperature ranges take care of different defects that are caused by implantation. So at 900 to 1000, we get there to resolve these dislocations, to completely get rid of those dislocations. The hotter, the better, but then it adds up to the cost of the process, right? But on the other side, if you do it too much for too long, they will start diffusing. So your profile will start becoming widened. So as a process engineer, then we have to know what high temperature processes will come afterwards once we have done implantation or diffusion. Because that will then dictate the change in the concentration for the post-heat processes. So I've done implantation, I made one structure, now I move on and I have to do oxidation. So the whole wafer goes in for oxidation, so I have to know that high temperature will cause that implantation to diffuse as well. So this is then accounted for the whole process. So instead of doing that drive-in or annealing for longer period, we leave it to happen for example, the oxidation process that's going to come afterwards. So layers that get to the surface, which make it all the way to the surface, can be healed back by what you call solid phase epitaxy. So this is the region where we get an epitaxy is deposition or growth of a film which follows the crystalline structure of the underlying layer. So with time, we can heal this guy, and what we are saying is, starting from here, we have get to this point, all the way we have healed the whole amorphous region, right? And what happens to the dopants? So they get swept into the new crystalline structure, right, which is forming, and they become active. If the layer is buried down, in that case it will occur from both sides. So crystalline structure from both sides will start making it crystalline again. Does it make sense? So we ended up having amorphous layer after implantation. So healing process results back into crystalline structure for us. And while it does, it also activates the dopants. So dopants also fight their crystalline places in that lattice to start contributing their carriers. So they have to get to their proper site. So this is the second function. One is healing, which is repairing the crystalline structure. The other is the activation. So again, defects are reduced, dislocations form, and some dopants get precipitate close to them. But then at temperature greater than 600, they fill the vacancy and become activated. So this shows the profile of temperature where they are getting activated as the temperature is going up. But then they also cause, the high temperature also cause the diffusion to occur. So if you have 2 times 10 raised to 50, so that would be the 3 regions defined here. That's the movement of the carriers. Phi is those in terms of how carriers are moving. So as the temperature goes up, their movement is much more to get to their dislocation points. So diffusion, again, we want that to be minimal, but as the temperature goes up, we see the behavior of diffusion. So it starts expanding. Right? Now, in this case, what kind of diffusion case will apply? Limited supply or limited reaction? There were 2 phases in diffusion where you have dry-in, where you have unlimited supply of dopants. Right? No, not dry-in, freedom. And then in dry-in, we don't have any more dopants, so what we have is just that it's diffusion limited, right? Diffusion coefficient limited, how fast we can. So which case will apply in this case? It's diffusion coefficient limited. And how was the plot for that? So there were 2 cases. One was where we would have something like this, right? And then there was a case where we had something like this. Are you guys familiar with these 2 plots? Right? So if this is depth and this is the concentration, which case will apply with this condition? Second one, right? So same dopants now will be just getting much deeper, but the overall concentration will be coming down. Do you completely understand the difference between these 2 cases?
Not really.
No, you should by Thursday.
So is it right to say annealing is limited by this?
It's diffusion limited, diffusion coefficient limited.
So annealing process is limited.
That's exactly what's happening, that you start with this profile, but then as the temperature is going up, you end up with something which is much more expanded, but your overall concentration is becoming less. Right? So this was what we call pre-depth. And of course, these are changing with time in this direction. And from this guy to this guy is also with time. As we go further in time, exposure to high temperature, with time, this is what happens. So if I call this guy to be at T1, this guy to be at T2, this guy to be T3, I can ask you, okay, how are they what would be their relation to each other? There are 1,000 ways of asking behavior here.
So the process of time for diffusion limited, for driving, with the process of time, my dopamines getting deeper, but
Yeah.
concentration being
So they'll be like flattening out, but traveling much more into deeper into the wafer, right? But if you have unlimited supply, which is then with time, you're basically just increasing. That's going to stay at whatever your concentration is, right? Whatever you're supplying to the substrate, that can't go above that, right? But they're going to be depositing and going to go much more and more deep into the substrate, right? So then you have to remember what is the limiting point, limiting thing here at this concentration. Why doesn't this go up? Because that's directly your CS, how much you're supplying in that furnace.
I have a question, so for pre-dip, does it go inside the substrate, or it just make a layer over the substrate?
No, it's going inside. How can it make a layer over the substrate? So that's where it's getting dissolved into solid substrate. So you have ions in gas state, and they are getting dissolved into the solid substrate. Right? Yeah. In modeling, we define it to be a delta function, right? Which is very high concentration, very close to the surface, to approximate unlimited supply of dopants in the gas. Right? So if you look at those equations, you'll see we consider it to be a delta function. So if you do it for too long at too high temperature, we start seeing diffusion, which we don't want.
So, Professor, you mentioned the below graph is diffusion limiting process.
So once you are pre-depositing where you have unlimited supply of dopant and you are getting all the dopants that you want into the wafer, then we cut off the supply of dopant. Cut off the supply. Now we are just heating the wafer to let whatever we got into the wafer to dry well, to get to the profile, to the depth that we wanted to go.
So apron is reaction limited process. The apron.
There's no reaction going on in this case. That was oxidation where we had to get oxygen to silicon and reaction as a thing. In this case, it's diffusion. They're just traveling towards lower concentration of substrate, which is essentially the other side. Right? So they're going deep inside the wafer. They're just traveling, they're not reacting. So their travel is diffusion coefficient limited. Whatever the diffusion coefficient is, that is, they can't go any faster than that. Right? So we have to get them too deep, we have to wait, do it for a longer period of time, but then we lose the concentration. So we don't want that to happen. So it's can't be modeled by the diffusion relations, because in this case now we have many more damages. We have many more local damages there. And that changes the diffusion of those species. It can retard them or it can make them slow. In case of boron, that is much faster. Right? But as the healing starts to come in, it becomes slow. So we can't use the same relation. And if you see that plot is also not as aggressively flattening out like in this case. Right? So in case of drive-in, we saw a much more distinct profile change. But in this case, it happens fast, but then it slows down as the damage is healed. As it's healed by high temperature. So that is what is called transient enhanced diffusion. So, which is advantageous for us, that we can get the profile that we need much quicker. So this can give us results which are not as per the model. So if you see as the temperature is going up, we see the behavior of dopant to be much more anomalous.
So is this something we want? Necessarily?
TET is good because you can implant a very thin layer and then you can diffuse it quick to the profile that you need. For shallow junction, yes, this is to our advantage. But uncontrolled is not something that we need. So what we call the SP was epitaxy, which was causing this what you call bringing the amorphous material back to a crystalline shape. It can allow much lower temperature for activation because the reformation of crystalline structure itself is letting the dopants to fall into the interstitial phase, to vacancies, to start contributing their carriers at very low temperature. Right? So this is then what is used to create ultra shallow junctions using pre-amorphizing implant. So we deliberately do implant of silicon to make surface amorphous because then we can create these dopants, active region which is very thin in depth using SP. It makes sense to make very shallow. Now these are inactive, so we don't care. They will not contribute to any device process. So this is this guy interface of the amorphous and single crystalline, and growth occurs to the left from here. So growth occurs on this side. So this is the region that is then electrically active for us. Very thin region, right? Which is good to make shallow junctions. And on top of shallow junctions, ultra shallow junctions. Very, very thin junction. So from annealing, there's now standard process what we call RTA, rapid thermal annealing. What it does is it spikes to a temperature for very short temperature. It essentially does exactly what we would do with just anneal, where we would gradually heat it up and keep it there for some time and bring it down. But so these are high throughput processing. So we can just put we can get bunch of wafers out very quickly. The whole batch comes out very quickly. And now in this case, this can be done for 1 to 20 seconds and get the same results. Yes, ma'am.
I think I'm confused. In annealing, do we heat it up and then let it cool down slowly? Is that what we do?
Why would we want to cool it down slowly or heat it slowly? Why would you just
So that
think about it?
the gradient, no, I just wanted to know if we do the cooling down slowly or not.
Yeah, so you tell me, should we want to do cooling down slowly or
Of
rapid?
course, no, it has to be slow.
Why?
So that there is a smaller gradient of it, like. There
That's how we
shouldn't be-
anneal metals, right?
There shouldn't be any abruptness in the temperature change,
There should not be any abruptness in temperature change. Why?
or else it will. Okay. In case of crystal growth, what happens is when it comes out of the melt, because of the change in the temperature, it forms a solid, right?
Right.
So I don't want that.
But this temperature is not that high that silicon will liquefy. Right? It's just, yeah, epitaxy is a process where they can reorient, but it's not a liquid
Right.
thing. But yes, but there's another some other reason why we don't want to heat them up too fast or cool down too fast, because then different temperature, what do you call, if you have a bunch of material on there, you have metals, you have oxide here, so each has its own, what do you call, thermal coefficient of expansion. So you can end up with a warped wafer, which is out of shape, which is not completely flat, and it happens. So depending on how much of what type of material you have, yes, that might be a consideration. How quickly, but we can work on reducing that effect, and that's why RTA works. That you heat it quick, cool it quick, and your wafer is still good. But why do we want to do it quick? To have high throughput, to make many more devices quick. The high throughput reduces cost.
Are we also reducing diffusion depth or unwanted diffusion by
So,
doing this?
what we are doing essentially with the very rapid anneal, we are reducing the unwanted diffusion. That's exactly one of the reasons why we want to do that.
But you don't cool it down quickly, do you?
So if you see the time, we don't cool it down quickly. Yes, you're right. So it can.
You spike it, but then you let it cool down.
It takes a while for it
Well,
to.
not that slowly, right?
Yeah, it's 30 minutes.
Yeah, but this is something that, cooling down is probably slow, but heating is where you get it to high temperature quick, keep it there, and then let it cool down. And it can be, the heat source can be many ways. It can be lamp laser or a bulb. Right, so once we do that, what we are left with is this. For different depths of silicon we get. So this is for boron, no pre-amorphization. So for different temperatures we get different activation. Right? So for different temperatures we get different concentration of boron, which results into different resistivity of the wafer. So what is the equipment that we use for implantation? We know by now they are large and they're complicated because they need to have number of different components have to come together to do implantation. So we need an ion source, we need a feed source which will be providing pumping in the material that we need for the ion generation. There will be ion extraction and filtration device that's going to get rid of the ions which are out of mass and charge range. Something you need to accelerate those ions, and then need to focus them to have a scan on the wafer. So we have a very tightly focused ion beam, and then we have to raster it on the wafer. And while we are doing that, we have to measure how much do we get on the wafer. So when I say measure, so that's the metrology. So that's, if we do that measurement while it's happening, we call it in-line metrology. So we measure it while it's happening, or we do offline, which is afterward. How do we characterize or categorize them? By current or by energy that we can implant. Right. So of course, low current or high current give us different doping that we can do. So this can do low dose implant, and we can do doses above 10^50, which are used for source and drain. And So this one can do batch, where we have ion beam stationary and wafers are rotating on a disk, and this one is where we put one wafer down and the beam scans over it. Again, same for low energy and high energy, that will cause deep or shallow implants. So if I need to do shallow implant, I have to use low energy implanters. I want to do deep, then we do high energy implanters. So these are some of the evolution of the ion beam implanter equipment. So now our current is way small, but our devices are also shallow. Right?
So when we talk about current, are we talking about electrical current or are we talking about ion current?
Current charge passing through unit area. So whatever we are using here, ions. So current and dose, there are two things which are interrelated. Right? Dose is, we looked at, it's a opposite of how long you do it, and how much charge you get transferred during that time. But current measures how much charge is passing through a unit area in unit time.
I say it doesn't matter whether the charge is an electron or a sodium atom or an arsenic atom.
Right.
Or
In
whatever.
one case, it's those that how many actually make it to the surface. In case of current, you are just looking at how much are passing towards your wafer.
I see.
Right? So for those, what we don't. If you think about dosimeter, we are not worried about how much is coming out of the source. We are worried about how much is getting to me.
I see.
Right? So same is the case. In terms of dose, you are looking at how much make it to the substrate. But in case of when you're measuring current, you're measuring how much is traveling to get there. So now over years, the beam current and energy has gone down, and essentially our requirements are also not too deep, right? So our requirements are also shallow, so we can get by with smaller energy and smaller current, right? These are just some examples of application. Source drain does. Okay, those things which I was talking about, which extend below the gate, are called source drain extensions. So those are also ultra shallow deep implants. So those are ultra shallow junction that we use, and contacts as well. So contacts we'll see once we go into the vias and interconnects. Contacts, we just need a very shallow region, but we need it to have certain area to make an electrical contact, right? And the reason is simple. We want contact to have very small resistance, right? So contact resistance should be very small. So and resistance then is a function of area. So we want that to be shallow, but we want to have certain area that we need. So over years, our requirements have changed, and so have applications. How do we monitor those? By total current that is collected by the collector within a cup. So you may be passing as much current, but what actually gets there is what is called dose. So we use something called Faraday cup. Have you ever heard the term Faraday cup? It's a cup type component which essentially gathers all the current that gets there, and we measure that. So we integrate how much charge over how much time has reached there. And why would current and dose may differ? Because your current may, your charge carrier, so ions may deflect, not actually make it to the wafer, or they might reform atoms and reach as neutrals, right? So they wouldn't give us the activation that we need. And they may be doubly charged, where they have added electron or got rid of some charge. So these are the inaccuracies which can happen to the ions before they get there. How do we improve it? High vacuum. And high vacuum results into something else which we have talked about before, reducing or increasing the mean free path. So reducing the number of collisions and increasing, an ion can travel without coming into contact and deflecting with another ion or another gas in the system. And we want to get rid of whatever comes out of wafer. What do you expect to be coming out of wafer? Resist polymer, right? So if you use resist as a mask, what would happen to the mask material once it gets bombarded with high energy ion? What happens to nail polish once you leave it drying for a while? It gets dried up, becomes even harder. So there is always solvent residues. There are chemicals which are there in resist. We haven't covered that. That's coming next. The resist itself is made up of 2-3 things: resin, and there is a photoactive chemical. So they can outgas. They can get knocked off. And once they come off, they can result into degradation of how much iron speeds there. So we need to remove them quickly. In most of the processes, you have to remember that we do a reaction, which may be etching or maybe deposition, maybe implant. We always have to get the product swept away from there to keep the reaction continue for the new fresh material to come in and do etching or deposition or doping. Make sense? So remember, you might be challenged to ask what are 2 requirements of etch. So it's not just getting the etchant to the substrate. Have we done etch yet or not yet? In case of implantation, it's not just getting the ion to the wafer, it's to remove the whatever outcast material is away from that wafer. In etch, it's not just bringing the etchant close to the substrate, it's removing the products also from there.
What is beamline pressure?
Beamline pressure
Loss line.
is the current signal response to changes. I don't know, I think this is more to how much charge is being pumped out of in the beam, probably, during current signal. Beamline pressures. I don't know, what does that mean? I'll look it up. What is beamline pressure? Beamline pressure. I'll see what's the actual idea here. Okay, so we are ionizing, we are bombarding the wafer with ions. It's going to get charged up. Once it gets charged up, it's going to repel the same charge away. So we need to neutralize the wafer as well while it's happening. So this leads to positive charge buildup, and have to get rid of that charge. So those charges not only come from the ion beam, but from the secondary electrons as well. So what we stream a low energy electron beam to neutralize that charge. So it doesn't deflect the charges, the ions that are coming towards it. So this is what is called electron shower on the wafer. So coming from this electron here. Okay, now this is what we were talking about, cooling. So during implantation, it gets heated up. We had to cool the wafer also during that process. So that's done by what we call backside cooling. If we don't, this is what's going to happen to photoresist. So you see all these cracks and deformation in the photoresist. And this is the case. There's no deformation in case we cool it from the backside. Right? So this, during implantation, that heating up can result into activating dopant and healing the substrate, but we don't want that at this stage, right? But because what we need is we want them to go to the depth that we want. We don't want them to be activated because that's gonna change the concentration of the profile, and then the resist reflow, which can result into the region that we want to be actually doped to change. Right? How do we measure? So inline metrology, it is a 4-point sheet resistance measurement, a polymer where we can see changes as it gets implanted, right? Or current voltage measurement of a capacitor made up on the substrate. So we can, during the process, we can measure these things. End of line process, this is called spread resistance profile or secondary ion mass spectroscopy. So we see how many we bombard ions and we see how many come out of the substrate. We measure that, so that tells us how much is what's the profile of implantation, right? So applications of implantation, of course we know junction formation. We control threshold voltage. We define channel stop where the channel finishes in the device. We form source and drain. We form wells with heavily doped parts. Punch through is an effect of short channel. So short channel is where channel size is coming small and their source and drains are overlapping. Or what we call graded source and drain formation, which was the idea that we don't want pocket of same concentration, but what we do now is we make different gradings of that concentration in that source and drain. So these are what we are most concerned, CMOS fabrication. Right? So this is the idea of SOI wafer, silicon and insulator, where we want to implant them deep inside. So there are two types of that. One is CMOS, another is called smart cut. Generally, CMOS is most common, what is called selective implantation of oxide. Stands for selective implant. I think that's what it is. Where we implant the oxide at certain depth, and then we have the silicon oxide which acts as an insulator, or it can act as an etch stop layer as well. So this is what we call buried insulator in this case, right? So these are just few applications which are, some are related to what we are doing, some are probably not so close. So where all the places do we do implantation? Of course, we do source and channel and drain, right? Which are 50 to 200 nanometer deep, and the concentration is 10⁻17 to 10⁻20. But then CMOS, right? Complementary metal oxide semiconductor. So complementary means we can have, what is complementary? We have N types and P types, both types of devices. But if your substrate is P type, how do I make N type devices?
You make an angle and
So we make a certain region where we just make that small region, very well defined region to be end-type. How do we do that? We implant there. So implant is not just for the source and drain, it's done to make that what you call well. That is triple well implant. There is outer well and then there is inner well. So there is different levels of implants that we do. So then these are examples of a number of tricks that we are doing to take care of short channel effects. SCE, short channel effect. We will not go into what are those, but we do these tricks to make devices still work even after scaling. Right? So short channel effect, as the name says, those are issues that have arisen because our channels are becoming too short, right? Because of scaling. So we have seen a couple of those issues where the space charge region or what you depletion region has started to overlap, right? So there are many more issues. Punch through is another one. We will not discuss that. I will not ask you what short channel effect, but we have to know that these tricks are done by implantation. So we do this punch through implant, this pocket implant, this contact implant where we are implanting some metal to make a contact with the outside world. Right? So we have sourced in extension implant, which is these ultra shallow extensions from source and drain. Right? There's retrograde channel implant where we have the concentration grade is changing. So we gradually bring it back to the background concentration. So there's this number of places where we do implants. And each implant is done independent from the other one. Can't just, so some of them may be, but most of them are done on its own. So we have to cover everything, do the alignment, open the window, implant it, activate it, move to the next step. Maybe do another implant for the other part. Right? So to tell you which one is more common, diffusion or implant when you make devices? Implant. There's without even looking at the simple reason, we can control the depth, we can have very shallow junctions, right? We can control the profile, right? So there are some simple reasons why. We had them listed start of last lecture, right? And that's why we want to do this. And we can use them, a number of materials as masks. So we looked at that last time also. The what you call trajectory, how deep the ions travel through different materials, right? As a general rule, we want our mass to be this thick, greater than this thickness. RP, how deep it goes, 3 times of the stratum, 3 times of what it goes on either side of that depth that we want it to go, right? So we can use oxide, nitride, photoresist, right? Polysilicon, metal polyamide, which is another polymer, right? To make our mask. And this tells us dopants and photoresist, how deep they go. And dopants and silicon dioxide, how deep they go. Right? And what is their spectrum, what is their sigma. Right? So if I give you this few pieces of information and ask you to define the mask for me for certain dose, certain dopant concentration at certain depth I want, should be able to design a mask for me. And when I say design a mask, you'll just be defining the thickness of which material we should use based on your simple calculation. Possible? at certain temperature. Make sense or not? Of course, we have exam next Thursday. You are worried. Not like if I ask for calculation, it wouldn't be something more than you should be able to do in the back of envelope, right? If you know where to look for what number. Does it make sense? The question would be to, that information is there, how do you synthesize that information to get a meaningful answer? Your calculation itself, if you see yourself with some square roots or under roots, then you have probably gone, you are too far from what I expect you to do. Just back of envelope, which would be, if you have 6.2 divided by 3, I'm okay if you estimate it to be 2. Right? That's back of envelope. You don't have to be exactly 3.12 because, does it make sense? For exam, your calculations, your
So you don't
inference.
need to bring calculator.
Oh, I don't allow calculator in my exams at all. So it means you don't have to use a calculator. If you end up with a number which has 4 numbers behind decimal, then you have screwed up somewhere. Should be simple. So probably we are close to finish anyway. So these are again minimum thickness of silicon dioxide or resist to arrest 99% of ions. And the S function of energy. And what else do we have to consider when we are choosing a mass material? Okay, let me stop it here. Resume slide. Right? So let's stop that. Let's keep these few slides out of. Questions?
So, scope of the exam, is it all the slides that have been covered so far plus the calculations?
Up till here.
Make an application also.
Plus the calculations. Have you done any calculation? Yeah, probably few and over. Right? But it would be from this plot, not sure. So you have to read the plot, get the numbers, use them in some simple relation.
One question on oxidation. In Dean-Group's paper, it is mentioned that diffusivity of water is less than that of oxygen. But wet oxidation takes place faster because the equilibrium concentration is more. But slides mention that diffusivity of water is faster than oxygen.
I think if it says diffusivity of water, probably that was not what it meant. It would be the diffusivity of vapor in the silicon is high.
It's lower than dry oxygen. That's what the paper says.
Okay.
But wet oxidation is faster because its equilibrium concentration at the surface is more than that of only oxygen.
Okay, I'll have to look at that myself. But I will not ask from paper. Whatever handouts I've given, stick to slides.
And okay, on the slides it says that 111 silicon crystal orientation, it is more than, I'm sorry, it is less than 100 oxidation of the rate.
Okay.
Shouldn't it be more? I mean, you have more atoms over
There
there.
are more. I have to look up what's the physics behind.
Okay, or is it that it's more dense, so it's difficult to break into that?
Okay, so then you have to remember the 3 phases. So once you get the top layer oxidized, maybe that's quick. But now they have to diffuse through to get to the interface.
Mm-hmm.
That's where the collisions might be more
Okay.
for the diffusing oxide.
So if it is
Oxygen.
denser, it is difficult to for the
To
oxygen to
penetrate.
pass through. Okay.
Yeah. That's it. Right? So we'll meet.